right, so here we are with lesson 22, resonant circuits. Now, before we get into the topic of resonance, I just want to make a couple notes. One is that this is kind of a new application of AC circuits. And what I mean by that is that so far we've kind of been focused on power and analyzing lots of different circuit configurations, all with the same frequency. So this new application is we're going to be changing the frequency, or considering if we could change the frequency, if we adjusted it. That's both lesson 22 and 23. What happens to the circuit when we change the frequency? It's no longer staying the same at 60 hertz all the time. We're going to be changing it. Its application is mostly in radio and communications. And so if you think about changing the dial on your radio in your car, you're actually changing the frequency that you're receiving. And so now let's talk about what is the resonant frequency. So if we think about that, so far we've been changing the circuit up. Now we're going to be seeing what happens whenever we find change the frequency and say that we'll like see how the circuit behaves. How the circuit behaves. All right, so what we're doing in this class is all series resonance. And all series resonance require R, L, and C, right? They can go in any order, but typically they're going to have a resistor, an inductor, and a capacitor. There are parallel resonant circuits, but we will not be doing that in this class. We're dealing all with the series resonance. So if we think about these two formulas right here, as far as reactance, the reactance of a capacitor and the reactance of an inductor, right? Another way that we could write them would be 1 over 2 pi FC, and this one would be 2 pi FL. And that F is the frequency, the omega is the angular frequency. But let's see, if we were to increase as F were to go up, what would happen, right? If I look at this formula, if F is going up inside of this one right here, then what would happen to the X sub C? X sub C, the reactance of the capacitor, would go down. And the X sub L of the inductor would go up. We can see that right here, XL and F. So as F goes up, XL would go up. And that's what this graph is showing right here. And it's linear, that as F goes up, XL goes up as well. And what happens to XC as F goes up? Right here on the right, as F goes up, XC goes down. And so the special frequency, if we were to overlay these graphs, is where XL equals FC. Actually, I'll highlight that so we can see it better, right? It is called the resonant frequency. So we're going to overlay these graphs here on this next page, and we'll see it right here, right? So this is the graph of XC going down, and this is the graph of XL going up. And essentially, if we set them to equal to each other right here, then we can solve for it, plug them together, and this is a tiny little proof. But this right here is the formula for the resonant frequency. Other times, you may also see it labeled Fs. You can think of that as the special frequency where this occurs. And essentially, what's happening, if we think about that these are all in series, right? I'll draw it over here on the right. If I have a resistor and a capacitor and an inductor, right? And then here is XL and here is XC. Well, the resonant frequency is where XL and XC cancel, and the circuit is purely resistive. And if you're thinking, this sounds kind of familiar like power factor correction, there is something being canceled out, but the way that we're canceling out, rather than adding more elements in like we did in the power factor correction, now we're adjusting the frequency. We're dialing the frequency until we achieve these being canceled out. And whenever these are canceled out, this is the next graph, the Z, if my Z is consisting of, my Z total of all three of these would be the R plus the JXL minus the JXC, right? And if those two equal each other, then all that's left is that the Z total is equal to R plus J0, right? And so if the R plus J0 is there, now we've minimized, right here, we've minimized the impedance. And what that happens is if we follow this down, these should line up. Right here is the other resonant frequency, is that the I is maximized. And what that says right there, it's maybe hard to see, but the I is maximized. So this resonant frequency, they cancel each other out. The result is purely resistive, and I is maximized. So if we think about that, if I'm stuck somewhere with a radio and I need to call back to headquarters and I want to achieve the maximum signal that I possibly can in order to communicate my very important message, then perhaps I go and I shift my radio to the resonant frequency based off my circuit components, and now the I is maximized, and so that signal is maximized. Now, the resonant frequency is right here at this peak, FR, also called FS, for the special frequency of the series resonant, right? But there is still some range where it's still very effective, right here. And that is from F1 to F2, and those are called the cutoff frequencies, right? The bandwidth can be defined as going between those two. And so we'll call F1 and F2 the cutoff frequencies. And so those are where it's still very effective at sending out the current. And what we'll see here is that that's at the 0.707 from whatever the Imax was. And so that's the limits of the bandwidth. Now there's another term that we need to know, and that's called the quality factor. And that's basically telling us the quality factor Q tells, you could say, how pointed or flattened, or just how pointed or flat the curve is, right? Whenever we have higher quality, it's pointier, and the bandwidth is narrower. Right, and so we can see they're saying right here, Q3 is the greatest sensitivity, and so we can even see the bandwidth is more narrow right here, and the graph is pointier, it's sticking up more. We have different ways that we can solve for the quality right here, and I think on the equation sheet it calls it QS, and it calls this FS. We'll flip over to the equation sheet in just a sec to discuss all these, because the other thing to note is that everything needed to solve for resonant is on the equation sheet. There's no other extra terms like in Thevenin where we need to think about processes. Everything that I need to know is on the equation sheet, as long as I can remember that the resonant frequency is, whenever I'm choosing amongst all the frequencies, which one's the best for this circuit, to minimize the Z and maximize the I.